And so let me briefly recap what we have been saying so far. So in this journey, in this short journey on graph embedding technique, we tried to find, to describe some methods that might transform a graph into a vector representation. So given a network with some nodes and edges, we were trying to find a representation, a vector representation, so that at each node corresponds a vector. And in this vector space, everything is simple. If we want to do classification, regression, or clustering, or whatever we want to do, everything, of course, is easy. We can use the standard techniques that we have been using so far. And we saw a first set, we said the first techniques that have been developed were somehow describing each node using some statistics. For example, the node degree, the centrality index, the clustering index, and so forth. So we can associate a vector to each node, and then we can have a representation. And the main disadvantage of this is that you could have the same representation, vector representation, might represent many different graphs. So in the end, there is no one-to-one correspondence, and there is no, and so this prevents from having good results. So we turned our attention to shallow embeddings. So in those embeddings in which we try to obtain a representation of the network using this other set of techniques. And we were defining this, we described the ingredients that we need, and we saw how characterizing the similarity of the nodes, the loss function, and the distance between the embeddings, the node embeddings, vectors, how we could end up in many different algorithms. And we saw also that we could use some level of stochasticity using, for example, we saw the example of the random walks in order to have more elaborate methods. Then we said, okay, but those methods have several limitations, transductivity, they are only transductive, so we cannot add new nodes. New nodes cannot appear in this graph. And then also the fact that somehow the representation of the nodes do not share any parameters. So in a way, this is a limiting factor in the possibility that we have to obtain very algorithms that can perform well in many different situations. So we turned our attention, and also we said we are only able to describe the topology of the network, the wiring of the network, but if we have some additional information, like we know something about the nodes, we have a vector of features about the nodes, this cannot be embedded, cannot be used to produce the embedding. And so we turned our attention to graph neural networks, and we tried to understand how these work. And so we were talking about this message passing that is implemented in graph neural networks, so how we aggregate information from nearby nodes, and also we also talked about the update, so which were the methods to have those updates, and specializing those two ingredients, let's say, specializing those two functions, we have the possibility to develop many different methods. And we were also analyzing how those GNN work, and we tried to understand from a theoretical point of view how they perform, so what they do. Somehow we tried to understand a little bit better what they do. And in the very last slides, I was proposing to rewrite actually the GNN using matrix operations, and we said this has the advantage of having very simple operations, matrix vector matrix operations, and this might be useful on one side because we have a very structured computational kernel, so this will perform very well on some specific hardware. On the other hand, this might be a little bit daunting in case I have a very large graph, because this means that I should store all the graph together, and this is not always convenient. I wanted to just to give one more bit of information on this to try to make a connection between those GNNs and the attention mechanisms that we were seeing this morning. So what does it mean, an attention mechanism for graphs? And also to try to create, but this will be somehow will be not very precisely stated with the transformers. So as we know, there are many, as we might know, there are many studies that are devoted to the extension of transformers to graphs. And to tell the truth, I was trying some of the available techniques that have been devised. The first of those was developed by some scientists at Microsoft, and they were calling it graphomers. But to tell the truth, I was not very lucky in getting some nice results on some specific instances of some problems related to economics and finance. So I really think that there is still a wide space to develop novel methodologies. So in the end, what we would like to do is to develop some novel methodologies that might somehow take into account the limited expressiveness of those machineries. So first of all, let me talk about the attention mechanism. You remember this morning there was another paper that was cited. Attention is all you need. That is a very famous paper that introduced this topic. It was 2017. But this idea has been present in graph neural networks maybe a few years before. But what do we mean by attention? Somehow, as we have seen so far in this message passing operation, that is the operation in which we aggregate the information around the node, we do some operations like, for example, computing the sum of the representation. Here is omitted the k at step k, but still is always the same. We aggregate, for example, computing an average or computing the sum and using some form of normalization, just to take into account the fact that we might have very different values in the vector in these HVs. So in the graph, the attention is implemented using weights. So we weight the contribution of the nodes that are around the node U using some weights. So learning some weights. So we will try to give more weights to some of the nodes that, in our opinion, let's say, are more important than others. And depending on the definition that we give to those nodes, we end up in some different attention mechanisms, and therefore algorithms. In particular, this is implemented in GATT, graph attention. Sorry, I go back one slide. That is this graph attention network. So this is the way in which we compute those weights. And again, we need some how do you say, matrices that we need to train. So there are many different proposals. Again, some work better in some contexts, some other work better in other. No one is solving all the problems. And also, there was an attempt to introduce this idea that is very common in transformers, that is the multi-head, attention, the multiple attention heads. That is popular, as I said, in transformers. So in this case, what we do, we generalize this attention, those attention weights. So now we have a tensor of weights that we need to compute, that we need to to obtain in order to obtain that are then used in the message passing phase. So there is a direct connection between what is happening in the development of methodologies that are devoted to text problems that are related to text processing and those that are related to graph. So whatever has been developed for text mining, let's say, has been partially developed in this realm. So I think that this is yes.
Variant property that we wanted to have. But I guess it does not.
No, for sure it does not, because because the expressiveness of those of these graph neural networks is not less of those that use mechanisms, attention mechanisms, is not less of those of the basic GNN. That is very limited, to tell the truth. But still, for example, those GNN, the basic GNN cannot, for example, compute very simple functions like the number of some subgraphs. They cannot approximate very simple functions related to the graphs, and also they are not able to distinguish two graphs that are very simple and that are different. This is very, very well known, but still this is not inhibiting this invariance, permutation invariance of the GNNs. So I think that okay, so we have been talking about this aggregation, this aggregate operation. We have seen that there have been many different proposals to extend these aggregations, and in one of those solutions that we got is GraphSage is one of those algorithms. On the other hand, the message passing somehow has been less studied, although the update operator is also equally important in this context. So we can look at this generalization of the update operator, and one important thing that I wanted to highlight and that was coming out in the discussion before is the fact that when we in the message passing, if we go too far from the node, what happens is that we are aggregating information from very distant nodes, and this has the effect that the representation, these vectors that we use to represent the nodes, are almost all the same. So we are not able to distinguish anymore the nodes in the graph, and this is called the oversmoothing phenomena. So to overcome this oversmoothing phenomena, there were some other proposals, and in particular there is this GraphSage which uses this concept of skip connection. I think there is the slide, the references in one of the previous slides. So this is more or less everything that I wanted to say with respect to a single network. But what happens when we have multiple networks? So if we have two groups of networks, let's say that we have two classes of networks, each of 100 graphs, and we want to build a classification model of those, so that if a new graph arrives, I can say if it belongs to one class or to the other. How can I generalize this? Okay, so there are many different applications. Let me change the set of slides. Yeah, this is exactly the last. Okay. Again, let me share. wool graph. So, okay. Okay, so now the only difference here is that we are adding this word, wool. So we are not embedding the node of a single graph, but rather we are embedding a complete graph. Okay, so we have hundreds, let's say, of graphs. We want to get a representation, an embedding of all those graphs. This QR code brings to the PDF of those slides. If you are not, if you don't have a mobile phone to get it and you want, you can ask me and I will provide the reference. You can search Mario Guarracino and you will find my email address. So, just to recap what I, this is always tricky, right? Okay, just let me recap what we have been saying so far. So when we talk about graph embedding, we are using this encoding, which associates to every vector, to every vertex node in the graph. It associates a representation, an embedding, and the decode operation, as we said, is the one that makes us that actually is used to understand what is happening in the neighborhood of a node. So this is used, for example, to do link prediction or node classification on nearby node, on let's say nearby nodes of the graph. When we talk about, and we have already said that node embeddings are used to study interactions among entities, and that there are several applications. But what happens if we want to make predictions at the graph level? So what happens if we want to learn a representation, so a vector, for every, we don't want, actually, we want not to learn a representation of every node of every vertex in a graph, but rather we wanted to learn a representation of a graph in itself. So now we want one vector for each graph. So in this case, if we use the same notation and we use this encoding, so the same idea, we have a class, a set of graphs, G1, GM, with the same set of vertices. So of course we need to fix this. We need to fix this, and a wool graph embedding is again a function that given a graph in this set of graphs associates a vector in RD. And of course, there are as many vectors as the graphs that are contained in G. And this encoding should preserve some proximity measures that are defined on the graph. So in this wool graph embedding, what we do is we associate to each network, to each graph, a vector, and once that we have had, so suppose when we have this family of graphs, let's say that we have two classes of graphs, we compute the wool graph embedding, and we end up in a vector space. So in this vector space, for example, we can do clustering, classification, or just visualize what is happening so far. As we might imagine, all the things that come here have been either come from graph neural networks or they come from other studies that regard a single network. This is I'm sorry, this example is not strictly related to the topic of the workshop, but we will have use cases in the next days. So we will have plenty of examples on how to use networks and family of networks, and I will also give an example in one of the talks in the following days in which we can use family of networks to describe a problem. So this is not a new thing. The paper was published in 2008, so people were using a magnetic resonance to obtain information about the signals that are produced by the brain. So this is so what we get is a diffusion spectrum of the signals that are emitted by the brain. And so once that we have the picture of the brain itself, we can segment it in various parts, and there are atlases that describe what the various parts of the brain do. So connected to each part of the brain, there are some specific functions, and what is interesting to do is to understand how those different parts cooperate with each other. Okay, so what we do, somehow we, starting from the signals that we get and associating them to specific parts of the brain, we try to understand how the different parts work, and somehow we obtain a network in which each node is a part of the brain, and they are connected if the brain is answering to some specific stimulus at the same time, is producing some signal at the same time. Okay, so we want to understand how the different parts of the brain cooperate with respect to some tasks. Maybe we are showing some image to the patient, or we want, for example, to distinguish some patients that have some neurodegenerative disease from patients that are healthy. So we will have a group of people that are healthy. We do the MRI, we map the signals using the atlas, we obtain the networks for those people. Then, these are the healthy, then we have another group of people, a cohort of patients. We do the same, and we try to understand what makes those networks different. Once that we know, that we understand why they are different, we can do the equivalent of a feature selection. So we can identify the parts of the network, the subparts that are somehow different from each other, in order to say, oh look, for example, the signal that are coming from this part are not activating this other part, and therefore this function is lost in this patient. There are many different examples of this. For example, we could in our DNA there are genes. Genes are encoded in our DNA. Genes produce a molecule that is called the transcript. They transcribe RNA, and those RNA are actually activating or disactivating, so overexpressing or underexpressing some other genes. So we can take two genes and we can connect in a network if the product of this gene is having an effect on the product of this other gene. Is either making it produce more or less transcript. But the same happens in metabolic networks, in which we have some reactions. The metabolism is a set of reactions in which some metabolites are consumed to produce some other metabolites, and they are catalyzed by some enzymes. So again, we can obtain a network in which the two enzymes are connected if they, for example, produce and consume the same metabolites. And there are so many other situations. So again, we will take a group and we will compare with another group in case of classification, or we can cluster the observations or do any other type of analysis. I will skip this because it's not really interesting for our purposes. So what are the viable techniques for Woolgraph embedding? So depending on from which point of view we look at the problem, we have different techniques. So if we have already seen that the graph embedding can be seen as a matrix factorization, so as a representation of the similarity among the nodes we saw for graph embedding, and the same happens for the matrix factorization. So again, we have Laplacian eigenmaps, and we have others. Then there are the methods that have been developed in the realm of graph kernels. So those studies started around 2000, if I remember correctly, 2008, 2009, and we got many of those. Then there are the ones that are based on neural networks. As we can see, we were talking before, for a single network of graph sage can be extended in the case of multiple network. I will only talk very briefly about 3 of those methods, and I will show you an idea that I had recently and that I think might be of interest because it might be of interest. It's a different way to do this. So with respect to the matrix factorization cases, we want to represent the graph. So what we have is that we can use, for example, the adjacency matrix to represent the matrix of each of those graphs. And so what we would like to do is to obtain a representation of we want to obtain the embedding starting from those representations. So suppose that we have a set of graphs, G1, Gm, again on the common set of vertices, and the joint embedding embeds all the graphs into this vector space with the dimensions, in which each graph is represented by a vector lambda I. How do we obtain this representation? We take the single adjacency matrices of the symbol graphs, we have M graphs, and we try to minimize this object. So the distance of those adjacency matrices to a matrix that is obtained through those rank 1's matrices, this linear combination of rank 1 matrices. So we try to obtain HK, the vector HK and the lambda I that are vectors, that have d dimensions, and we try to minimize this quantity. So we end up with a representation, each lambda I, we have one lambda I for every graph, for the M graphs. These have d dimension, k varies from 1 to d. So we end up with a vector a vector for each graph. So what are we doing? We are somehow looking for a single matrix that is as close as possible to all the adjacency matrix of the various graphs. Okay, and we can use this for downstream analysis. This was published in 2019. These are actually a little bit older. So graph kernels are a little bit older. We know that kernels can be used as to compute nonlinear embedding. So this is very old story. No? Kernels have been around since the end of last millennium. And somehow they provide a nonlinear, they can be used to compute a nonlinear distance between objects. And what we do, we use graph kernel to obtain this embedding. There are different ways to do so. One example is the shortest path kernel. So using the shortest path kernel, we can compute the distance between two networks. And if we compute for every network its distance to all the other networks that are available, then we have a vector representation of this network. So this is so we are computing every possible distance between every possible pair of graphs G1 and G2. So in this case, what we do, we transform those graphs G1 and G2 into graphs S1 and S2, and in which there is an edge between a pair of nodes of Si if so if there is a path that is connecting those two vertices in graph G. And once that we have this representation, so this S matrix will have the same number of nodes that has the original matrix, and two nodes are connected if there is a path that is connecting the two nodes, for example, with a fixed distance or whatever. And so we can compute the distance between this kernel, with this nonlinear distance between those two matrices that represent the two graphs, simply computing this sum. and where this wall, this K is a kernel. This means that it has to be a positive definite kernel, so that we are in the hypothesis of the Mercian theorem. And this has several advantages with respect to the fact that you can represent the result in a finite dimensional space, because in general you end up in an Hilbert space that might have infinite dimensions. So let's go to, then we have this graph to vec. This is derived from node to vec. That was one of the methods that I was describing for the graph embedding. And this is based on a very simple idea. This is based on an algorithm that was obtained to do classification of documents. So somehow what we have here is that we associate to each document a representation of the words, so one vector for each word, and this doc to vec provides an embedding for text. We have been describing this with different techniques this morning for text classification. I don't know if you remember that we said that BERT could be used to classify documents, to obtain representations that were useful to classify documents. So what happens is that you represent a document using a set of words. Starting from this set of words, you obtain a vector representation. So the idea was to substitute this part in a graph using another technique. So using another technique to represent each part of the graph. So we look at some subgraphs, 1, 2, C subgraphs, and using this graph to vec obtains a representation using the same idea that is behind doc to vec. So a graph is viewed as a document, and the subgraph of degree D, we have been calling this, so that are the subgraphs that are rooted in each node and that contains all the nodes at the distance, at most distance D. And starting from this, we get somehow a text description of the graphs. And this is obtained using those two algorithms. As I will not go into the detail of this, but this is very interesting. It's a very interesting idea, because what we are doing is we are again exploring the neighborhood of a node, and we are obtaining a text describing the neighborhood of this node, and this text is the composition of the node labels that are present around the node. You see here what we are doing. We are aggregating the nodes one after the other. And so this is a very interesting idea. So what I decided with some colleagues, what I decided to do 2-3 years ago, was to use this idea of doc to vec to obtain an embedding. So to use this NetPro, so we developed this methodology to somehow to represent graphs. I will show you just a very simple example of what we do. So suppose that we have this graph. Okay, so we have 7 nodes. We have some weights on the edges, and we compute 2 distributions. This is called the node distance distribution. Let me see if I can make it a little bit larger. Okay, so this is called the node distance distribution. So we sit in a node and we say how many nodes are at distance 1, 2, 3, 4, and so forth from the node on which I am sitting. So I am computing the fraction of nodes that are at a certain distance from the node in itself. Here the nodes are weighted, so these are not integer numbers. These are not exactly fractions, but they are weighted by the weight, and and we decided which was the size of the bin. So 1 means a certain specific distance. So what we end up is in a representation. So we take those numbers and we sort them. So since 2 and 4 are larger, we consider node 2 and 4 first, and then we add the label 1 and 5 to this word. So we create words starting from this node distance distribution using the labels of the nodes. So here we have NDD because we use the node distance distribution. Then we use N1 because we are representing N1, and then we start using the nodes. So the node labels to create the words. So we get one word for each node, and this represents the description of the graph. So the set of words that we are using to describe the graph. Then we give it to Doc2Vec, and Doc2Vec does the machinery, the skipgram, and produces the embedding. And we also use this other distribution. This is a transition matrix. So if we sit in a node, we say, which is the probability of starting from N1 to reach, for example, N2 in one step? Okay, so the probability, of course, of a random walker sitting in N1 of reaching N2, we have to sum is 2 because this edge has weight 2 divided by the sum of the weights, and so we get 0.2. And we continue. Again, so now we are embedding, we can repeat with the different length of this shortest path of dimension 2, and so forth. And then again we form these words. So the corpus describing the graph is the set of words that we have been obtained starting from some empirical distribution, probability distribution, describing the graph. So this in a sense can go as far as we can. So in a way, we are describing, it's not a local description, this is a local description because we are saying, no, it's 1 hop, 2 hops. This is more related with the topology of the network, so we can go as far as we want. And what is very interesting is that when you do this, you get very interesting results. We used a very simple. Data set. So we used 1,600 networks. This was obtained by the generator. Santo is talking in the next days by Lancichenetti, Fortunato Radicchi. This was a random graph generator that was used to test community detection algorithms. So it produces graphs that contain communities. You can fix the number of communities. You can fix the density of the edges that are inside. You can fix the number of edges that are connecting the different communities. For example, here we have 1, 2, 3, 4, 5, 6 communities. We have 5 communities. Here the connections are much denser than here. Then we have 600 of those networks of this type, 1,000 of networks of this type. And we want to see if we can build a machinery that can discriminate the two. So a classification algorithm that, given a new graph, can say it is of this type or the other type. So we applied this. So in this picture we have this is a t-SNE representation. Is a kind of PCA representation. Each point is a node. Each point is a graph. So we have as many points as the number of graphs, 1,600, divided into classes, red and blue. And this is the result of that we obtain using the node distance distribution. Since these are distances, we were using only node distance distribution, only TM1, only TM2, or a combination of those. And this refers to the overall accuracy, the tenfold cross-validated accuracy that we obtained on the embedding of those graphs, not in this space, but in the embedded space. And as we can see, in some cases, you can be very precise, very accurate in classification, although the two classes are unbalanced, to tell the truth. So somehow, I think this to say what? That there are many opportunities to improve those methods and to develop novel methodologies in this field. For example, this node distance distribution, we could use, for example, Jensen and Shannon divergence between the node distance distribution of two nodes to compute a weight to produce a new attention mechanism. Right? We can say two nodes are close if their node distance distribution are close using some distribution measure, whatever we want, and therefore we can weight the contribution of the different weights in different ways. So, in my opinion, there is a large space for methodological development for full graph embedding. For single graph, there are so many papers that is sometimes it's even difficult to make a bibliographic search. Now, at the last the ICML conference, there were, I don't know, more than 100 papers on graph neural networks. So it's very difficult to keep up to date. They are very small modifications. As we have seen, they are tiny incremental updates of the method. So it's very, in this case, the situation is, I think it's a little bit easier. And as I was mentioning, there are many different problems that can be somehow that can be modeled using multiple graphs. So I am happy that we ended up a little bit earlier and that there is some time to discuss. If there are questions, please. The microphone is there.
Mario, I wanted to ask you just completely randomly, so you've talked about whole graph embeddings and you've talked about node embeddings. Is there something like an intermediate step where you embed half the graph?
Wow. Why not? So there are examples of subgraph embeddings. So I don't know if this is intermediate or comes before single graph embedding. But I don't know what would be an intermediate. Edge embedding. Why not? Yeah, that is done. Yeah. This is a good point. So edge embedding might be in between.
Actually, a really related question. How sensitive is this to how much of the graph you know? Like,
how sensitive is this to?
To how much of the graph you know. Like, if you only know 90% of the graph, how accurate is it? If you only know half the graph, what happens then?
So very interesting question. So the only thing that I tried to do was actually empirical. Because this is very important, for example, in cases in which you have data poisoning or you have, so somehow, yeah, in case of data poisoning, so suppose that you have a system that learns from graphs. And suppose that somebody is trying to cheat, so somehow to introduce some graphs that somehow change completely your models that you build on top of this. So how much the model change, how robust, let's say, are those models with respect to the poisoning of graphs? And this depends, of course, very evident if you take a graph that is completely different from all the others and you plug in the training set, everybody will see it. But if you take a graph that is very close to the one that you have in your graph, then it will be more difficult to find out, but it might spoil to your system. So this to say that there might, because your question is related to the fact that you might have, that you only know a part of the graph. So this is the closest thing that comes to my mind. So small perturbations in a graph, how do they alter the results of the embedding? This is what I've been doing. If you have a partial knowledge of the graph, you can only embed that. But how sensitive is the embedding to this partial knowledge? I'm sure that there is something, but I need to search. Because I am sure that I read something, but it doesn't come to my mind right now. Very important point.
Just
Yeah.
thinking out loud here, I think it goes back to the graph neural networks question. How you only observe a part of the graph and you want to infer the rest.
Yeah.
You want to infer the existence of edges. Edges that were not bounded. But that's very active research, I think.
There is also subsampling. So in a way in which you only use a part of the nodes to train your GNNs. So in this case, but in this case, you do it randomly. Yeah. But you should do, but this is still a random sampling. So if you don't know a part, it depends, and you want to compute the embed, how sensitive is the embedding to the fact that you don't know a part of the graph. It depends on why you don't know this part of the graph. Do you don't know it at random, or you don't know because fixed parts? So I think that it will make a difference depending on the way in which you are subtracting this information to the method, to the embedding method. This is my understanding. But this is very, very interesting question. I would like to go through and see if there is anything done.
Thank you very much. So well, maybe it is a very trivial question. I'm not sure about that. So there are some ways for embedding whole graph using some sort of augmenting the individual node embeddings, right? But there are some readouts function which somehow combine different node embeddings in a clever way and then find out a single vector, right? So is it proven that, let's say those kind of embeddings are reducible to node embedding, whole embedding reducible to node embedding? Is that proven that these kind of embeddings are not reducible to node embeddings, or might be?
No, the answer is no. I don't know any paper that describes no, and I didn't know. So it's a good way. It's a good field to explore.
Yeah, because if it is, I mean, it's completely new thing. If it's not reducible, then it means that it's completely new thing, global thing. So it's very, very interesting.
Yeah, I don't know. I don't know. Thank you. Okay. Of course, there is still time to discuss. They will not kick out.